Force equals mass times acceleration, the law of universal gravitation, and given their mass and distance times a constant. As the distance increases, the force gets smaller by the square. Two main kinds of energy, kinetic energy and potential energy. In plain English, energy of movement and stored energy due to some circumstance. For example, when you held your phone, it stored gravitational potential energy due to being held above the ground at a certain height. Once you dropped it, that potential energy was converted into kinetic energy as the phone fell. Then it smashed into the ground, and the phone absorbed some of the energy, making the screen go boom. Work is defined as force applied over distance. Work is force applied over distance, and since you didn't move the weight at all, no distance means no work. The conservation of energy. Current, voltage, and resistance. This is Coulomb's law. Wait a minute, this is just Newton's law of gravitation in disguise. These four equations explain pretty much all of electromagnetism, but first one states that if there is an electric charge, there will be an electric field, or this big E, emerging from it. Add another and you have an electrostatic field. These lines tell us in which direction a charged particle would feel a force at any given point. The second one tells us the same for magnetic fields, and even though electric charges are cool and can be alone, magnetic poles are not. They're very lonely, and there will always be a north pole together with a south pole, and a single pole can never be alone. Okay, now here's where things get kinda freaky. You know how electric charges only act on other charges and magnets only affect other magnets? Well, that's only true if they're not moving. The third and fourth Maxwell equations tell us that a moving magnet creates an electric field and a moving charge or electric field creates a magnetic field. We assume the speed of light is constant because it arises from two other constants. Energy and mass are kind of the same thing, he added, which explains why atom bombs are so freaking powerful. According to this formula, even just tiny atoms can release a humongous amount of energy by giving up just a fraction of their mass during fission. What is fission? It's the same thing Oppenheimer used to make this thing go boom. You see, there's two main ways to gain energy from changing nuclei, fission and fusion. Fission aims to split the nucleus of an atom into two or more smaller nuclei, which is most often achieved by blasting the core with neutrons. Fusion is the opposite, where you combine two smaller nuclei to get one bigger one. The energy came from something we call a mass defect, where the resulting nucleus is lighter than the starting nuclei. This missing mass is what was converted to energy during fusion. All energy comes in tiny packets, or quanta. Schrödinger gave us an equation that gives you a probabilistic model of where you can find it if you were to measure. Heisenberg's uncertainty principle. You can never know both the exact position and the exact speed of a quantum particle at the same time.